Hi, my name is Mike Kelly. I'm VP of Advanced Packaging Technology in Amcor, and it's my pleasure to be here at the Samsung SAFE Forum for 2020. I was here last year as well. Great exchange of ideas, so really looking forward to it. Going to talk to you today about heterogeneous IC packaging. It's a new and developing arena for combining silicon functionality into a package. And just going to briefly touch on some market trends as we see them in the OSAT space that are driving some of our customers and end products in this direction, and then do a deep dive in where we are and some of the particulars with regard to solutions in the heterogeneous space. As everyone knows, the data and data-centric model of operation with data at the edge and data processing taking place in the data center is well established. This impacts a lot of different arenas in high performance packaging, including networking, as the systems are beginning to move to 400 gig, in the compute space for servers and storage, and also the AI deep learning algorithm training that is taking place in the data center. This is a very virtuous cycle. So these algorithms are trained in the data center with a monstrous amount of data. Those algorithms are optimized and then compressed and made available out at the edge or in smart devices for that matter. More data being created back into the data center and so forth. So a very virtuous cycle. This is a slide that's typical for today. The main message here is data growth has just exploded, over 25% CAGR. And the video content in absolute terms is just staggering. So the impact to silicon. So of course, silicon is being driven. Die sizes we're finding are not necessarily shrinking. Even in the advanced nodes, large die sizes are becoming fairly common. And this is causing people to look at the cost of individual die and is there an opportunity to do something to lower cost, including die partitioning. Power density is going up. Even though power per transistor is coming down, we still see total power density per square millimeter of functional silicon going up. And this is causing this interest in heterogeneous integration. We've already seen some of the products come out to market. Some of the early integrations were ASICs or processors with high bandwidth memory, and nowadays also discrete SerDes devices for really high-speed, long-reach SerDes. This is a quick snapshot. On the left-hand side is transistor density. As we all know, transistor density is improving nicely. It's a little off of the forecast that Moore had years ago, but it's certainly not dead. Perhaps it hasn't kept pace with that forecast or that algorithm, if you will. But maybe even more importantly nowadays is power density still increasing. So yes, power transistors are coming down, transistor power is coming down, but the net of it is in per square millimeter of silicon area, power is still increasing. So temperature and power dissipation continues to be a big challenge. Very quickly, yielded wafer costs are going up. The yield increase from 14 down to 7 is on the order of 1.5 to 1.8, depending on which data you see. And design costs have really exploded, both in validation and physical design, but also in software costs as well. So if you focus in on the IC packaging piece of it, what does it mean? So definitely there is a segment where higher memory bandwidth is a requirement, and most especially in the AI market with the advent of HBM, HBM1, 2, and 2E, and now HBM3 is on its way. A very high bandwidth product at a reasonably low power, and I/O counts are going up. So the idea of getting more I/O into a switch device for the networking space is driving things as well. In turn, the shrinking operating voltages inside the silicon is requiring a better power development network, distribution network. And so that is translating into an impact on IC package constructions as well. increasing dissipated power, as I mentioned, and this kind of translates over into the packaging space as memory being co-located in the package. The higher I/O count is causing some customers to look at discrete SerDes I/O silicon, so those become chiplets, if you will, inside the package. And then with regard to managing power supply and managing supply voltages, definitely IPDs and even some voltage regulator modules that customers are looking at. And the improved thermal dissipation solution, there's only so much you can do in the package, but we have invested heavily in some of the metallurgical TIMs to help make even higher dissipations possible. There's a term going around nowadays called data locality. It's nothing new, but it is becoming even more important as power density and total power dissipation is going up. This is just a very quick comparison, but if you compare HBM to off-chip DRAM, that's about a 10x improvement in the type of power required to access that memory. And then if you're going on chip in cache, whether it's L1 or L3, again, almost a 10x improvement in power. So where data is and how far you have to reach out to it is really driving package construction. One of the things that this typically boils down to is the type of interface, whether it's a parallel interface with a lot of physical wires or a serial interface with fewer physical wires, but a bit stream that's serialized down one physical wire. And the impact on packaging can be pretty intense. In parallel interfaces like the HBM data bus is a pretty good example. That's a 1024 wide bus. And so that requires a 2 micron line in space typically to get that bus routed in a package. On the serial interface side, typically there can be fewer physical wires, and so that may not drive the packaging routing density quite as hard. Definitely there are trade-offs. Typically the parallel interfaces are lower latency and lower power, and so that's a trade-off against packaging complexity. So what does it mean for packaging? It means basically we need to get ready and are in the process of qualifying different packages to address heterogeneous package content. If they're parallel interfaces, if it's HBM or some of the chiplet buses that we have seen recently, you're going to need to be in a module technology, whether that's 2.5D TSV or substrate SWIFT, which is our trademark for what we for the high density fan out category, or if it's S-Connect, which is Amkor's sub 2 micron excuse me, line space bridge technology. Serial interfaces typically, but not always, can have their routing accomplished in the package substrate itself. These are typically cored ABF buildup type package substrates, and sometimes coreless, and even some of the hybrid coreless. And then that can be a really solid solution if your routing density will permit it. What we're finding is more and more products need finer line and space than you can purchase in a high-end ABF type substrate, in a build-up substrate. So that kind of is the impetus for the heterogeneous integration. This is a very high-level depiction of the two competing paths, not really competing so much as being complementary. On the left-hand side is the substrate path. We all know that. That has been the go-to technology for a good long while. The SoC flip chip BGA has been tried and true for a long time. We've taken that into multi-chip modules over, the last couple of decades, really. And an offering that we're also in the process of making possible is a molded version of that, which has some advantages, we think, for multi-die packages. And then even stacking substrates. So because, especially in the networking space, but other applications too, the main substrate that it typically has a 1 millimeter pitch going down to the motherboard, that is becoming a very large substrate. So 85 millimeters used to be the biggest we'd ever see. Nowadays, there are customers have 100 millimeters on the books. So being able to stack a high density ABF substrate at a tighter pitch down to a lower cost, lesser density substrate for the 1 millimeter pitch down to the main board is sort of the objective there. On the right-hand side is the RDL, the HDFO, LDFO and HDFO fan-out approach. So all the way from SWIFT, which is a high-density fan-out, onto a multi-RDL organic dielectric type substrate, up through SIP, which is a dense application of the same technology, and then even into a SWIFT construction for 3D. The final application is for higher end packages. The 2.5D interposer is there, is tried and true, it's high yielding, and a version of that using the substrate SWIFT multi-layer fine line RDL is what substrate SWIFT is. And then lastly, we are working on a version of the S-SWIFT with a bridge. And the bridge is intended to replace some of the SWIFT layers or some of the HDFO high density fan out layers with a bridge, either silicon or another material, and take some of the routing requirements out of multi-layer RDL, replace it with the bridge. For some applications, it's a really good use of that technology to come up with an overall cost picture that's lower cost. In the 2.5D space, we have been in HVM for almost 5 years now. We have a full TSV reveal capability. We have processed silicon interposer wafers from all the major fabs, full thickness wafers, thin the backside of the interposer wafer, do the die attach, mold the wafer, and then attach that to the package substrate. This is a snapshot of what is going on today in HVM. All of these are combinations of high bandwidth memory of one type or another and an ASIC or a processor. We are qualifying today packages with 6 HBM, and we're working on test vehicles with 8 HBM2E on them. So that has been a product that has been very successful. It is very solid. It is yielding extremely well. It is a go-to vehicle if you need to integrate HBM into a product space. This is just a quick snapshot of the 8 HBM version. The interposer, as you can imagine, is very large, 53 by 45. That is a big interposer because you've got to get 8 full stacked DRAM HBM packages as well as 2 ASICs on the same interposer. So on the fine pitch copper pillar, the go-to bump today has been a 25 micron diameter, 45 micron pitch, or in the case of HBM, 55 micron pitch is very typical. Normally we use copper, nickel, and a lead-free bump. We have experience all the way down to a 30 micron pitch bump and a 15 micron diameter. That is typically with a higher density copper pillar between 2 die, where that kind of density between the using those bumps in the die interface is required. Okay, the next thing I'd like to talk to you about is what we're calling substrate SWIFT. That's Amkor's term for high density fan out solutions. High density fan out is essentially a fine line multi-layer structure comprised of polyimide dielectrics and copper traces. Our maximum module size is 55 by 52, and typically for applications where you're combining die onto an interposer, you're going to need something like 2 micron line in space, 3 micron line in space. Our substrate SWIFT offering is capable of 4 layers of 2 micron line in space. Applications are various. I would say there is a move now early on to use it in HBM applications, but certainly anywhere you need to combine die, especially if they are fine pitch copper pillar bumping, this technology is a good option. We've seen a lot of interest in it in the networking space, but also in just combinations of chiplets for future processors. This is a typical cartoon cross-section. You can see the module is up here. It's a multi-layer RDL, or the interposer portion is essentially analogous to that found in 2.5D. In this case, it's an HBM, a 2 HBM ASIC combination. That module is molded and then soldered down to the substrate, just like 2.5D. Over here, you can see the scale. So the cartoon is a little bit deceptive. The actual scale here with the silicon, the micro bump, and then the very fine line HDFO layers are, only 30 or 40 microns thick in total. And then this would be one of routing on the circuit board itself, on the package substrate itself. So 2 to 4 layers. Everything we're seeing today is 4 layers, 3 or 4 layers, 2 micron line in space, up to 4 layers, and good electrical properties. It's a polyimide dielectric, so it's a better electrical system than the silicon oxides found in 2.5D. So this is just a quick status snapshot of where we are today. We've qualified 2 internal vehicles, one with a large 2-die split, which required 3 layers of 2 micron RDL, and another one with which is an ASIC and HBM2 construction, 3 layers of 2.2 RDL, a 4-layer construction. We've passed all of our internal engineering qualifications for that package. Our SWIFT yields are looking very good, better than 98% on the fabrication side. This is a die's last process, so we fabricate those layers first. If there is yield loss, we don't commit the expensive die to those sites. So it's a good way to make sure that you're building only known good sites. Today, we're in the process of doing a full product qualification with a functional ASIC and 2 HBM, and we expect to have that qualification completed by the end of this year. This is just a cross-section at 1,000 cycles, showing the really fine line buildup. As you can see, this is a dummy HBM and dummy ASIC with lots of daisy chains, so it's easy to assess for open shorts and quality of construction. And you can see the really fine line multi-layer RDL down here in these other pictures. One of the things that we really like about the HDFO approach is that its warpage profile is a lot different than 2.5D. It tends to flatten out. The module tends to flatten out at reflow temperatures. And so this makes managing the module warpage, especially if you are large and have several or many die in there, a better proposition for us on the assembly side. We think it's got some headroom for growth there. So just to wrap it up, this full functional status is in the works now. We have yields up beyond 98% on our 2 micron line space, and we're looking ahead for production parts. Our look ahead production parts did an OS pass, but our full product qual is expected to be done this year. Very quickly, this is just the progression of the heterogeneous in the substrate SWIFT space. Starts with substrate SWIFT up here, which we're working on today, and taking this all the way into an HBM construction, which is the product we're working on today. We are developing and prototyping now our so-called S-SWIFT with HBM and a bridge. With the bridge in place, we often call this the S-Connect technology, which that bridge can be silicon, it can be other materials as well. And so it's got a lot of flexibility. That particular space in the package is essentially 3-dimensional. So you can have a bridge down there, you can have IPDs down there, potentially you can even have other functional silicon chips in that path. And then true 3D hybrid bonding is definitely in pathfinding mode inside of Amkor. Very quickly, I'm going to just spin through some of the electrical advantages. I'm going to focus on the fact that you essentially have a high-speed channel and you have power delivery that needs to be taken care of at the same time. Insertion losses for traces in the RDL technology and the RDL dielectrics are always lower insertion losses, electrically beneficial for managing that kind of loss. But lately we've been taking a look at the power delivery network and where do you need to locate bypass, power supply bypass, to be really effective in managing your voltage supply. And so there's a number of different places that you can put it. You can put it in the core of the substrate. You can put it on top of the module. But what we're finding today is you really need to put it under the SWIFT layers, under the HDFO, if you will, and get it in very close proximity to that I/O PHY that's either on the memory or the ASIC side. And this is just showing insertion loss. And with the case of having those capacitors located in the substrate core, you run into some pretty nasty resonances up around 60 gig. If you put them, if you do put them down underneath the module itself, you get a much better looking impedance profile. So that's the goal, and that is the plan for next year, is to basically take those into a developed package readiness category. Positioning wise, this is how we're positioning these particular technologies. For HBM all the way up to HBM3, most likely the silicon interposer, which is a silicon oxide type of interposer, a dielectric will be able to handle it. If you need to go faster than that, the polyimide dielectrics are a better dielectric system. And, you know, that really strikes home in die splits and today in chiplets. So there are some die-to-die interfaces that are running anywhere from 10 to 40 gig. So, you know, those trace runs obviously need to be short, and you need a decent dielectric. And we think that's a really nice place for the, you know, the polyimide dielectrics, which are present in the substrate SWIFT technology, to perform. Very quickly, just a snapshot. Today, we're working on the ASIC plus HBM. Size extensions are on the plan for next year's development, as well as the embedded caps and IPDs and high density bridge. Essentially, these two technologies follow very similar package construction to derive that three-dimensional space where the IPD cap can be located, or the bridge or the bridge can be located. So just to conclude, for 2.5D, yields are high. It's in HVM today. If you need to combine HBM2 or 2E, we have both of them qualified today. We have a full MEOL reveal and assembly capability, and we'd love to talk to you more about it. Substrate SWIFT is a HDFO technology. We think it has a lot of good potential in addressing some of the classic 2.5D applications, but also more of these discrete I/O chiplets and other chiplet combinations that customers are beginning to talk to us about. We're targeting to have a 98 plus production start on our first product. Our first high performance is a challenging ASIC plus HBM combination. And with that, I'd like to thank you for your attention, and I look forward to discussing with you later.